Hello again, Godot users. On today's Godot Tidbits, I want to talk about saving and loading games. And normally I like to keep my tidbits fairly short, but as I started preparing my slides and kind of getting into the groove of what the quote-unquote right way to save a game is, I realized this was going to become more of a deep dive rather than a tidbit. So bear with me, this video might last a little bit longer than my normal ones, but we're going to go through how to save your games in Godot the right way, or at least what I consider to be the right way. So, scenario. You're playing around practicing your pixel art and you come up with a cool little futuristic catamaran boat and a torpedo, and then you come up with this cool mine, and then you explode the mine. And you think to yourself, all I really need is some water, my cool boat, couple of shores to not run into, some simple UI elements, and boom, I got myself a game. And I could call that game So you get your game all set up and you start to test it, and you can move around, and you can shoot the mines, and everything's going well. And then you think to yourself, I want a second level, and I want people to be able to save the game. How do I even start? Well, you make a UI, and then what? Well, that's what we're going to talk about today. Basically, what we need to do in this case is we need to learn how to save game object info out to external storage. We need to learn how to load that game object info back into our game and apply it to the necessary objects. And then we really need to learn how to work that save game logic into your game design from the beginning so that we're not trying to shoehorn some game design in at the end where we're going to have to change a million things and lose our minds. So here's how we're going to go about learning that. First, we're going to talk about the various save methods that are already available to us. Then we're going to kind of get into what we want out of this project. Do we want to use one of those built-in save methods, or like number 3 here, do we want to make our own save method that works better for the way we think? Then we're going to kind of lay out this project in pseudocode. Then we'll go back through and fill in the technical bits. And then we're going to talk about, game design for saving from the beginning instead of the end. And lastly, we'll make a game to use our project. We'll probably use the little boat mines demo that I just showed. So go ahead and grab the essentials and let's get started. You're going to want some water to stay hydrated. You're going to want some snackies around to fuel that brain. Go ahead and set an alarm and take some breaks now and then, because if you try to just bulldog your way through the whole tutorial, you're going to stop absorbing information at some point. And lastly, get that rubber ducky. Programmers use a rubber ducky or some sort of figurine, and they set it on their desk, and when they run into a corner, they talk the problem through with the rubber ducky, and more often than not, they come up with their own solution without ever having to go to external feedback. Back in Godot, we're going to go ahead and just create a new blank project because we're going to want to create something here for our save game project that's reusable and modular. And we don't want to do that within a game that already has a bunch of stuff in it. Now that we have our new project ready to go, let's go ahead and talk about some of the save methods that are available to us built in right out of the box in Godot. The first method I want to go over is just the built-in file access.storeVar. Basically, Godot allows you to store pretty much any variable out to a file, and it's really simple code. You basically just call the file access.open to open your file, and then you're going to file.storeVar and whatever the variable is that you want to store. Now, the benefit of this is pretty easy, but as you can see down here, the actual save game data file contains a bunch of binary that's not really useful to us for debugging. The next method is something called a custom resource. Basically, resource is a class that you can extend just like you can extend Node2D. And you can create a custom class that extends a resource just like you could create a custom class player to extend Node2D or character 2D. Basically, this allows you to have certain variables that you're going to store things in when you save the game, and then when you go to call your save game function or method, you're basically calling the built-in resource-saver.save on that class. Now this is a little bit better because you get nice human-readable text as the output, but as you can see, we're having to specifically declare everything we want to save, and since we have probably like a player and an enemy and a bullet or mine or something, this could get really complicated really quickly. Another method that's pretty handy, and one of my favorite methods before I really started diving into this, is simply to use a dictionary that you then convert to JSON and store out to a file. A dictionary is basically a key value pair that you can create within the GDScript, and then you can store whatever keys and values you want inside of there. So basically, if you create a save data dictionary and then set the key player global position X to your player's global position X, that translates into a nice text readable industry standard data file that you can then save and load, and everything's a little bit better there. This is not the perfect solution because it's prone to typos, and then you wind up having to have maybe a different save game file for your player versus your enemies, or you're going to have everything kind of spaghetti monstered into one large save game.json file. So even though this is a step in the right direction, it's still not exactly what we're looking for. So that pretty much covers the three methods of saving game data out to file that are built into Godot. We've got our file access store_var method, which is easy to implement. It's hard to scale. Well, I'm going to say it's not scalable at all. You have to read the variables out in the same order you put them in, and the output file is not human readable, so it's impossible to debug. And, well, actually, there's a side conversation we could have about whether or not a save game file should be human readable. There's a side that says it shouldn't because then somebody could come and hack it, quote unquote, and basically give themselves infinite lives. But that's a completely different conversation. You have encryption and other methods. I would prefer to have my save game data human readable because while we're developing a game, being able to debug is more important than keeping somebody from modifying a save game file on the fly. Enough about that. Second method, our custom resource and class, is another step kind of in the right direction. It supports built-in types such as your Node 2D and 3D. It's easy-ish to scale. Not really. You're still going to have to modify your class every time you add something in your game that you want to save out to file. It's nice though, because whenever you write a custom class, you do get the autocomplete where you hit the dot while you're typing something and autocomplete options come up for you. The output file is human readable, if not a bit obfuscated. But there is a concern for script safety because that .tres file does have the ability to run a script when you're loading a save game from disk, and you could have a bad actor that gets a hold of a save game file and inserts his own script in there, and then many bad things happen. And then the downside there is if you're going to scale it, the flip side of that coin is that you're going to basically have to have a custom class for every entity that you want to save, unless your game is ludicrously simple. So our final method that we went over is a simple dictionary that is exported to a JSON file. It's industry standard. You could basically transfer it up to a REST API if you wanted to have some cloud interaction going on. The output is very human readable and nicely organized. JSON is widely supported. The downside is when you're making your dictionary keys, that opens you up to typos because the dictionary keys are literally just strings that you type in, and it doesn't support as many types. The custom resource supports basically all of the built-in types in Godot, whereas JSON is more of, I think it only supports strings and numbers and booleans, and that leaves out a lot of the stuff that's built into Godot. So all three of those kind of fall short in one area or another, and I think that means the best solution is to kind of roll our own. So let's take a second and kind of write down what we want to get out of this wonderful save game utility that we're fixing to write. Back in Godot, I've created a simple text file so we can just kind of jot down the goals of what we want this project to accomplish. Firstly, we want it to be modular. We want to write this thing in kind of its own directory, and we want to be able to copy and paste it into any of our game projects without having to do a lot of modification to it. We also want it to be easily configurable. We want to be able to change the file name of our save game file, or change the group name of the objects we want to be eligible to save. We also want this to be mostly unaware of what data is being saved for each individual node. Now, on the global scale, game-wide, we do want to have some mandatory save game implementation in place so that we can have it kind of like a custom class, and we have auto completion and stuff like that. But as far as the individual 2D node 2D that's being saved, we want to allow the developer to determine the data that's being saved for that particular node and handle all of that logic within the GDScript that's attached to that node. Furthermore, we want to be able to save both static and dynamic nodes. And that's pretty important because static nodes never really leave the tree, and dynamic nodes can be spawned or despawned, etc. And just for sort of a visual representation, let's take an acorn squirrel game. Don't worry, I didn't make a guitar riff for this one. We have our player who is static. That means he's going to enter the tree when the game is launched or the level is loaded, and he's not going to leave the tree until the game ends or he dies and the level is reloaded, whatever. Our enemies are dynamic. That means they are randomly instantiated and they move around the screen and they leave the tree when they die. Similarly, our bullets are dynamic. They are instantiated when you hit the throw acorn button or when the enemies have their throw acorn method called, and they fly across the screen and they leave the tree when they either leave the screen or hit our player and cause damage. And now that we understand that, we can kind of gather that the static and dynamic objects are going to be a little bit different in the way we apply that save game data back. The static objects, we're just going to apply that data back to the original object, but the dynamic ones, we have no idea how many dynamic objects have been instantiated or deleted since we last saved the game, so we're probably going to wind up just wiping out all of the dynamic objects, and then for each one in our save game data, we'll instantiate a new object and apply that save game data back to it. And both of those should work even if the game is reloaded from scratch. Next, we're going to want to lay out some basic ground rules for the nodes that are going to be saved to our save game file. Back in our visual aid, we can lay this out as the player will need to wave his hand and say, I want to be saved. And he's also going to say, please, when you're restoring, make sure I'm in position first, because all these enemies over here are going to be targeting him, and he needs to be where he is going to be as they set their sights. Next, we have the enemies who are also going to wave their hands and say, save us as well, and you need to restore us second, because we need to come in after the player is positioned, and we're going to then target his position and start throwing acorns. All of the bullets / acorns are going to want to be saved as well, and they're going to say, hey, you know what, restore us third, because we want everybody in place before we start flying around so that we have some nice fleshy body to smack into. And then lastly, the little nernies around the scene, the decorations, are just going to say, no, we're good. We don't need to be saved because we're not moving, we're not interacting with anything, and we're pretty much just fluff for the scene. And as that translates into our ground rules, only nodes that need saving should be involved. That way, if we have a whole lot of static elements in our scene that are just for decoration, we're not wasting CPU cycles and disk space to save stuff that's just going to be spawned and static when the level restarts anyway. Each node needs to be responsible for its own data. We talked about this when we were talking about file save types and the way we were going to roll our own. Basically, we want a nice infrastructure in place to where we can save our main game data out, but each individual node that's going to raise its hand and say, I want to be saved, needs to be able to provide its own data, such as position or target or one of the myriads of things that a node could care about when it's saved and restored. Lastly, the node should be able to request its own loading order. It's something that it should be able to pass in with its saved data. And our utility should take that requested load order into consideration when loading the data. And the last thing I really want to jot down here is I want this to be able to store and change the running scene if necessary. A lot of the tutorials only deal with one simple scene, and saving and loading happens within that scene. I want to be able, with this utility, to store the currently running scene that the data was saved at, and that way if we have a project with multiple scenes, the save and restore utility should be able to switch to the correct scene before restoring all of the information. Now to conceptualize the save phase of this utility, we're going to start off with the utility announcing I'm going to save. We're then going to pass around this centralized entity here, and every object that wants to be saved is then going to pass in its save game information. And then once we have all that information accrued in our centralized entity here, we're going to dump that out to file. For the load phase, we're simply going to pull our information back out of storage, do some basic data validation on it, and sort it in order of priority. We'll then iterate through all of the objects that were saved in order of priority. And for any static objects, we are just going to send out a load notification saying, hey, we're fixing to load, prepare yourself. We'll then pass whatever data that object wanted saved back to it so it can restore its original state. For the dynamic objects, we don't know how many of them are going to be in existence at the time of the load, so we're going to send out a load notification. The dynamic objects will be expected to delete themselves. We will then handle reinstantiating all of the saved dynamic objects and pass their information back to them so that they can position themselves and restore their states in turn. Now that we've kind of conceptualized how this is all going to flow, let's lay out some basic requirements so that we don't get kind of confused down the line later. First of all, we're going to want to pause the game during loading to prevent stutter, and then be sure to unpause it when we're done. We'll probably work that in as an option that we can toggle on and off. We're going to want to use a class to handle type safety, because we get autocomplete and then we can't assign the wrong type of variables and stuff like that. But we're probably going to also want to use a JSON dictionary to handle the readable storage so that we get the nice human readable text at the end. When we're dealing with nodes to save, let's see, we're going to need them to probably be in a save group since we only want to save the nodes that need to be saved. Static nodes are going to need a way to refer back to themselves because we've got unique IDs and stuff like that. But remember, we want this to be able to load and save even if we've exited the game and started up again and the static node has been respawned. Maybe it gets a different ID during runtime, whatever. So we'll probably use a single member unique group name for that. And just to sort of visualize that, here we have our save group. Basically anything that's in the save me group will be called upon to submit their save data when we go to save the game. These two, the lemur and the acorn, are dynamic objects, so that's all we need them to do is be in that save group. For our static object, we have the save me group, and then we have this unique squirrel group. Now this should be a single member unique group so that we can call that group and expect only one object to come back, and then we always know how to find our squirrel when we go to restore its data. Going back to our requirements, remember we talked about having some sort of game-wide save data, and we'll kind of flesh out the structure here. So first we're going to want some version information, and this is to allow, if we update our game, we're going to want a utility to bring old save game data into the new format if we make any changes on that front. So we'll save a version number. We're also going to want to save the current scene info when the game was saved. That way, if we're in a different scene, when we go to load, we can first change to the correct scene before we start handing out save game data. And finally, we're going to want an array to store save game info for each object. This allows us to compartmentalize the save info, and it also allows us to sort that array by priority once we go to load. And speaking of individual save nodes, we're going to want some mandatory save game data for each node that wants to be saved. We're going to need to know whether that node or object is dynamic or static. We also need to know where that node came from. If it's a dynamic object, we want to know the resource path so that we can reinstantiate the object as needed. If it's a static object, we need to know that unique group name that we talked about earlier so that we can find that exact static object to pass the information back to. We also need to know where in the hierarchy that object existed during the save. This is specifically to where we can instantiate objects back where they were in the tree. And finally, we want to know the load priority so that we can pass the data back to the player before we start instantiating the enemies who are going to target him. We're also going to allow for each node or object to pass in their own custom data, but that's not going to be part of this mandatory requirement. And finally, each node or object that wants to be saved needs to have some required methods or functions. We're going to need an onSaveRequest function, and that's going to allow us to pass around that centralized entity that we talked about and allow each node to pass in the mandatory data. We'll also allow them to pass in custom data, but that custom data is going to have to be handled by the node itself. For the load phase, we're going to break it up into two parts, a load request and an actual load. During the load request, that's when the static nodes need to prepare to have their states restored, and the dynamic nodes need to clean themselves up and remove themselves from the tree to prepare to be replaced. Then during the actual load phase, the node is going to have to understand any custom dictionary it submitted and got back. The node needs to handle any faults in that dictionary, and then the node needs to handle its own data safety. And then as it receives that data back, including the mandatory data above, it's going to have to handle positioning itself and stuff like that after being reinstantiated. So I think in order to pull this off, we're going to have to come up with a sort of hybrid solution here. We want to use a class so that we can have our statically typed mandatory information in there. This will also allow us to save an array as part of that class. And then in the array, we have our object save for the individual nodes or objects that are going to be submitting that mandatory data here and the custom data. And the beautiful part of this is as long as we write some sort of method into our class that handles converting it to JSON to spit out to a file and handles converting that JSON back into class data when we go to load, I think that will solve all of our problems. Well, in the words of Zoe Washburn, talking ain't doing, so let's get started on this. We're going to go back to our editor. We're going to create a new script. We will call it global save. We'll open that up for editing. And let's talk about doing a class versus an autoload here, because I think we're going to wind up doing an autoload. Now our options here are class and autoload, and for our purposes they're sort of similar. But the reason we're going to use an autoload with this global save utility is that a class, which we create by declaring a class name keyword at the beginning of our script, does open up a sort of global presence and autocomplete and stuff like that throughout our code. But remember that we were talking about retaining the ability to change scenes when we go to load, and a class isn't going to help us with that. In order to change scenes, we're going to have something that exists outside of the current tree, and that's going to require an autoload. Now, autoloads could warrant their own dedicated tutorial. In fact, if you want one, let me know in the comments and I'll whip something up for you. But for the purposes of this tutorial, an autoload is merely a script that you write that extends at least node, that you then go into project settings, autoload, find that script, name it, and check that you want it to be a global variable. When you do this, whatever you named that autoload will appear as a class that you can use throughout your code. And the way this is different from the other class is that when you run the game, if you look over in your remote hierarchy, you'll notice that the main level, whatever you selected to be the startup level for your game, is going to be its own node as a child of root. And then your autoload will appear as a sibling of main, also a child of root, and it exists outside of what you would consider like get tree. And this allows you to change levels, which would change main to another node, or restart the level, and the autoload sitting outside of that tree will be unaffected. This is going to be essential when we go to change levels when we're loading a game. Something to note is that you do not put a class name when you're writing an autoload. You could, but you don't need to, and if you happen to put the same class name that you're loading with your autoload name, you're going to start getting errors. Now I know that's a lot of talking, but the takeaway is that in order to allow us to change levels when we load games, we are using an autoload rather than a simple class. Back in our code editor, we'll just get rid of all of this stuff and we'll start laying down some pseudocode. First, we'll just add a comment noting that we should load this script as an autoload name global save. That will allow us to keep the naming consistent when we transplant it to other projects. Next, we'll need a section to hold our configuration. Then we'll throw in a placeholder for our main interaction functions. This is where we'll have our save and load game methods. Then we'll have the methods that interact with the nodes or objects themselves. We'll also need a place for our file or storage interaction. We want this to be modular because we obviously want to save to disk, but maybe later on we want to save to cloud or something like that. And finally, a section to hold our subclasses, which we'll use as kind of templates for our main global save information and our individual node or object information templates. Now let's start by filling in our configuration section. We will begin with our version information that we discussed earlier. Then we will want a default for our save name. We will basically be adding .json to this to create our file name. We'll also prepin the user colon / prefix that you'll see later on. We'll also need the name of the save group that we'll call when we're going to ask nodes to prepare themselves for saving and loading. We also talked about pausing and unpausing the game while we're saving and loading. We'll go ahead and throw a toggle in here so that we can set whether we want that to happen inside of our logic or whether we're going to handle it outside in the game logic itself. And then to wrap up the config, we're just going to store our method names in some constants here. This will help prevent typos and allow us to, when we're doing the call method to our group, we can use this to fill in the method names that we're going to be calling. For our main interaction section, it's going to be pretty simple. We just need a save game function and a load game function. Now, I'm a big fan of type safety, and we're going to go ahead and fill in the parameters that we're going to use here. But just a word on type safety, if you're not using GDScript in a type safe manner, I strongly recommend using it in a type safe manner and using type hints and casting. If you're unfamiliar with this, you can look through the Godot script references, and they have a couple of pages on that. I've also got a tutorial on type safety and typecasting out there if you want to go through that. I'll try to put a link in the description. But the gist of it is, if you declare your method return types and your variable types as you bring them into your code, it allows you some autocomplete niceness, and it also allows you to flag any potential errors in the code editor itself so that you don't get surprised during runtime. In this particular instance, we're going to need a save name for our save file. So we'll bring in a parameter called save name. We'll declare that it is going to be a string, and we'll give it a default value if nothing is passed in. And in the spirit of type safety, we'll also declare the value that we expect to return from our method. In this case, we won't be returning anything, so we'll declare it as simply void. And the load game will get the same treatment. Now we'll come back and fill in the meat for those methods in a little bit, but I want to go ahead and get kind of the infrastructure laid out here because we're going to be using a couple of submethods and subclasses here, and I want to get those laid out so that we don't have that constant red line of error following us throughout our code. Moving on to our node interaction, we're just going to need a couple of methods. Let's have one to gather our save info and another to restore our save info. In the interest of type safety, we'll come back and declare our parameters and return types after we've filled in our subclasses and submethods. We'll also fill in a couple for our file or storage interaction, and that will consist of saving our dictionary to file and loading our dictionary from file. Lastly, we'll set up the subclasses that we're going to use for our global save information and our node save information. And we will just create those and name them accordingly with a global save template and a node template. Let me just add a few lines in there so that we can see a little bit better in our zoomed in view, and then we'll start with our node template and kind of fill in the meat and bones of our infrastructure working back towards the top. Now, with our node template, we want to cover some basic information such as, are you dynamic? This is part of the mandatory information that we had declared that we needed earlier. Are you dynamic? Where are you from? This is going to be the resource path or the unique group. Where do you go? This is going to be the parent node information. Do you need to load before or after other entities? And then any more info, and this will be the custom save information that we're going to allow the individual nodes or objects to provide. And basically the player or static object is going to reply accordingly. I'm static, here's my unique group. I am a child of main, which is our currently running level. I need to load first. I am going to store my position and health in my custom information. Then our dynamic objects will answer something like, I'm dynamic. Here is the resource path I come from when you need to reinstantiate me. I was a child of main, which is the currently running level, before I remove myself. I need to load second so that the player already exists and I can target him. I'm pretty much just going to store my position and my target in the custom information. So to fill that in our code, let's go ahead and declare the members, they're the variables that we're going to be using for our mandatory information. We will have our isDynamic, our node source, the parent node path, and our load priority as an integer. And then to allow for our custom information, we'll go ahead and create a custom dictionary. Remember that the node or object is going to be responsible for both populating and interpreting this dictionary. So all we're doing here is saving it with the rest of our save game information, and then providing it back to the node or object when we restore it. Then we'll need a couple of class methods to facilitate converting our information to and from a dictionary, since a dictionary is the entity we'll use to store our information as JSON. So we will go ahead and declare a method toDictionary, and we will specify the return type as dictionary. We will declare a variable as an empty dictionary, and then we will add the dictionary keys and values for our dynamic node source, parent node path, load priority, and custom dictionary, and then we'll return that dictionary. The reason we're not interacting directly with the save file at this point is that we want to allow for modularity here. So basically what we're going to start off with is our class with its own information. We want a method to convert that to a dictionary. Then we'll have that dictionary as a modular entity. We can then simply call json.stringify if we want to store that string to a file, but it also allows us to go ahead and later on add encryption or decryption or server storage instead of file access, storing it somewhere in the cloud without having to go through and rewrite a bunch of our code. And providing a method within our class to convert our class information to a dictionary allows us that sort of modularity. Moving on to the other direction, to populating the class from a dictionary, we will create the method fromDictionary, and we will specify that we are taking in a dictionary as a parameter. Now, we had talked about some sort of data verification and sanity checking, and I think we're going to do that here within the class. We had kind of indicated that we were going to do it right when we read from file, but let's go ahead and do it within the class so that we're not dealing with a bunch of random text from a JSON file when we're doing our sanity checking. To facilitate that, we will come down here and we'll create a section called Utilities, and the reason we're doing this down here instead of within the node template itself is because we're probably going to wind up reusing this within our global template as well. I'm going to create a method called verify dictionary key types, and this is going to be for our data verification. It's going to take in a dictionary. This will be the dictionary that we're verifying. It's going to take in a key type map, which is basically going to be a simple map saying isDynamic needs to be a Boolean, node source needs to be a string, etc. And then we're going to return a string. Basically, this is going to act as an error message. If it's blank, everything went accordingly and our dictionary should be good. Otherwise, we will return an error message in there and we can act on that later. So we'll start off with our return error message being blank, which would indicate no errors. Then we'll iterate through every key in our type map. We will pull the type that we are expecting out of that type map, and then we'll jump through a simple if-else statement. If our dictionary doesn't have the key that we're looking for, we're just going to say, hey, we expected this key and it is missing. Otherwise, if the type of that value that we got out of that dictionary doesn't equal the type that we're expecting, we're going to return an error message indicating as such. And then finally, after we're done iterating, we will return that message. And if it's blank, we know everything went okay. And if we have a message, we know that that's going to be an error. And don't worry too much if you didn't follow along with all of this exactly. I'll leave it up here for a second so you can read through this, but you'll see how it's going to work when we go back up to our from dictionary method and start using it. And I just realized that I scrolled off the bottom of the screen there, so let me just bring that up. And that's all you really missed, was return the error message. Now moving back up to our from dictionary method within our node template class, we can go ahead and implement this data verification. And we will do that by declaring a dictionary that holds our expected data types. Just as we talked about before, we're going to make sure that is dynamic is a Boolean, that node source and parent node path are both strings, that load priority is, well, wait, why aren't we using integer here? That's because JSON just stores numbers as numbers, and when you load that back, it's interpreted as a float. And so we're using type float here just for this data verification layer, even though we're going to use it as an integer later on down the line. Lastly, we're just verifying that our custom dictionary is of type dictionary. Remember that the individual nodes or objects are responsible for interpreting their own custom dictionary, so this is all the verification we need to do here. And since we're cool people and we put our verification logic in a reusable sub method, we can just spit out a one-liner to execute it, and we will assign that return value to a string. Now, if you watch here, we're going to turn red there, and if we zoom out, we can see that identifier global save is not declared in the current scope. And the reason I wanted to show you this, and the reason I didn't fix it off camera, is because if you run across this, it simply means that you have not registered your script yet as a class or as an autoload. To do that, we're just going to do what we talked about earlier and go to Project Settings, Autoload, find your script, and then make sure that the name is correct. And you'll notice that we standardized on global save with a capital S. We could just change that here, but let's go ahead and change it here. We're going to rename our script to put an underscore in the middle of it, following good naming practices, and then we'll go do it again. We'll go to Project Settings, Autoload, and we will close that out and refind it. And with the underscore there, it automatically capitalizes the save for us. We then click Add, make sure that our global variable is enabled, and close. And if this doesn't automatically fix itself for you, all you have to do is get rid of the end of this line and start typing global save. You'll notice now that it appears in autocomplete because it is now registered as a global class or autocomplete. And so then we can just Control-Z a couple of times to bring our line back to the way it was. And the IDE now understands that we're dealing with a global save global class that we can use. I'm not going to go through and show you the hierarchy because we don't have a current scene to run now. But if you go jump back to the part in the video where we were talking about it, if we did run our game, it would then appear in the hierarchy to the left as a sibling to the main running scene, and that means that we can use it throughout our script as a global class. Enough babbling about that. Now we just grab that error message and make sure that it's blank. If it's blank, everything went like we expected. If it's not blank, we're going to push an error message and let somebody know that something went wrong. Now, if we're going to handle that error message in our code, that's fine. If not, we still want to be able to act on whether or not this loading and verification went appropriately. So let's make sure to go up here and specify that we are returning a Boolean. And that will, of course, alert us that not all return code paths are returning a value, and that's fine because we're still going to come down here and do a couple more things before we return our default. And really all that's left is to, now that we've verified our data, we're going to go ahead and assign that data back to the field values within our class. Once we've done that, we can be reasonably sure everything went to plan, and we will return a true, which will not only complete our task for the from dictionary, but eliminate the error message. And that'll about do it for our node template. Now, while we're in here, let's remember that we do have some data types that are native to Godot, but don't fit easily into the JSON data structure. JSON can store strings and booleans and numbers and even arrays, but one of the main things we're talking about storing to the save file is position, and that's a vector too. So what we're going to do while we're in here is, since we know that node template will be passed into the objects or nodes that are going to be saved and restored, we'll go ahead and add a couple of helper methods here to help with data conversion. And for a position, or any vector2 really, that's as simple as creating a method called vector2 to array, which takes in a vector as a parameter and spits out an array with the x value and the y value as the only two numbers in that array. And conversely, we have a vector2 from array method that takes in the array as a parameter and returns a vector2. We do have a little bit of sanity checking here, making sure that our array is 2 in length. And if it is, we simply recreate that vector2 using those two numbers and return it. And if it's not, we just return a vector2.0. This should not ever come into play because we can be reasonably sure that the array that we're dealing with was created by our partner method. Now we have a placeholder and an infrastructure to go ahead and extend this as needed. For example, if we were working on a 3D game, then we would have methods to convert vector3s to arrays and back, and then any data type that is present within Godot that we need to store in JSON, all we have to do then is come back here and create the appropriate helper method. And that will wrap up our node template for real. Now let's move up and start working on our global template. Here we're just going to add those mandatory fields that we had talked about earlier. We're going to store the version as a string and the scene path as a string. Then we're going to create an array, and that's going to hold the node templates that the individual nodes or objects are going to pass in during save. Now we will be adding the toDictionary and fromDictionary methods just like we did with the node template. But remember that we also said that we want to be able to sort those nodes by priority. So let's go ahead and add that method just because it's the new guy, and we'll do it first. So we'll create a function called sort nodes by priority. It does not return a value, so we'll specify void here. And the beauty part of arrays is that they can have a custom sort function that basically declares that the A value and the B value will return in a certain order. If you do a comparison, that returns a Boolean. And I won't get too far into it, but trust me, this will sort your array of node templates in order by priority. And note that since we are using less than here, that we will have our nodes sorted in highest priority first, in descending order. Now we can move on to our toDictionary and fromDictionary methods. For the toDictionary method, again, we're declaring dictionary as the return type. We're creating a blank dictionary and populating the key value pairs with version and scene path. For the array, it's going to be a little bit more complicated though. Arrays or subarrays in dictionaries are null by default, so we're going to create a blank array as a separate variable. Then we're going to iterate through our save nodes, which we'll be populating during the save and load call. Each node is going to convert itself to a dictionary and append that to the existing array. This will give us a nice JSON compatible dictionary, and since we modularized it down here, it makes our code up here much easier. Then once we have this array populated, we can just add it as another key value pair to our existing dictionary and return the whole thing. And then for our fromDictionary, we will again specify that we are bringing in a parameter that is a dictionary and returning a Boolean based on whether it was successful or not, just like we did below. We have the needed types dictionary. This is sort of the same, where we say version needs to be a string, scene path needs to be a string, and save nodes needs to be an array. We are running our verified dictionary key types like we did before, and making sure that the error message is blank, pushing an error and returning false if something went wrong. Now that our data is verified, we go about the same method of assigning our values back to our field variables. And then again, we iterate through the array that we have stored in our dictionary and populate the array in our save nodes with those templates. Notice that again, we're using our modularized code, and that makes it nice and easy for each template to convert itself from the dictionary as we iterate through this list. Once we're done with all this, we will have a nicely populated global save template with version, scene path, and a populated array of saved nodes that are in the correct class format, so we can return true. And we're done with that section. Loading should be about as easy. Once again, we are going to take in the save name as a string. The difference being that with this method, we know we're going to be returning a dictionary, so we'll specify it there. And then for the meat of this method, we will once again prepend the user : / to the front and the .json to the rear of the save name. Then our save file will be the same file access.open, except this time we will specify the read flag, since we'll just be reading it and won't be spitting anything back out to the file. We will declare our JSON string as getAsText. This method simply reads the entire file in as a string and returns it. We will remember to close the file, and then we will again use the built-in JSON package, but instead of stringifying, we will be parsing the string back into a dictionary. Then we will return that dictionary to be used to recreate our templates. Cool. So with our file storage interaction out of the way, we can move up to gathering the save info and restoring our saved nodes. The gathering save info will be fairly simple. We know that it's going to return a global save template, so let's declare that as our return type. And then for this one, it's just a few simple lines. Basically, we will declare a new template as a global save template. The .new just creates a new instance of that particular class. Since it is a class, that new instance will have access to autocomplete, so we can say new template scene path, which is one of our member field variables, is equal to getTree.currentScene.scene file path. This will allow us to store the currently running scene in our save info so that we can switch to it later if we need to. The other field value is the version, which is statically assigned up here, so we don't need to worry about that. And we're ready to populate our node template array. To do that, it's as simple as getTree.callGroup, which allows us to call a method on an entire group one at a time. We will specify the group as the save group that we specified in our configuration. The method we will call, since we stored it as a constant, we can just use that variable here. And then the new template.saveNodes is what we're going to pass into each individual object so that they can apply their save information to that array. Once we're done calling that method on the entire group, we'll have a populated template and we can return that to whoever asked for it. The restore method is going to be a little bit more complicated. It's just going to do stuff and not necessarily return a value, so we'll be sure to specify void as the return type. It is going to need to take in a parameter, which will be our template, that is the global save template. Then we'll start filling in the meat of this particular method. We'll start with a simple sanity check. If the length of the template isn't any greater than 0, we're just going to say, hey, we didn't have any saved nodes to restore, and leave this particular method. We're doing this as a warning, not an error, because if we don't have any saved nodes to restore, that's not necessarily the end of the world. Next, remember that we are going to send out a loading request notice. This will allow the dynamic nodes to clean themselves up and remove themselves from the tree, and it will allow the static nodes to know that something is fixing to get loaded so that they can remove any references to dynamic objects that they may have, etc. Then we're going to sort the nodes by priority. Remember, we took in a template that is the class global save template, and down in global save template we provided a sort method. We're executing that here, and once we've done that, our node templates are all in order of priority from highest priority to lowest priority and ready to restore in the proper order. Now we're ready to iterate through all the nodes that need to be restored, and I really tried to do this line by line, but I can't type and talk at the same time, so I'm just going to paste it here and talk you through it line by line. We're going to start by iterating for node info, which is a node template because we're doing type safety, in template.saveNodes. This line is going to iterate through our sorted node templates in order from highest to lowest priority. Inside that loop, we are going to create a restored node as type node this will hold the new node that we are either instantiating if it's dynamic or passing information back to if it's static. So then if we're dealing with a dynamic node, we can expect for all of the dynamic nodes to have removed themselves from the tree. So we're going to instantiate this one and add it to the tree. So if is dynamic, we are going to create a node scene variable, and that's going to load from the source as packed scene, because remember we were storing the scene path as the node source in that particular save game data for the dynamic nodes. We're then going to instantiate that particular scene and save it as our restored node variable. Note that we're not forcing type here because we already declared it as a node up here. And then just for some sanity checking, we're going to attempt to add the new node as a child to the parent node path, which we took in when we were saving everything. So parent node, we're going to use a method called getNode or null, which is very handy because it gets the node just like getNode does. But if the node doesn't exist, instead of erroring out, it simply returns a null value. We'll try to get that node from the parent node path that we have stored, and we'll get it as a node for type safety. Because we use getNode or null, we can then check if that value is null. If it's not, we're good. So we're going to do parent node.call deferred, add child, and the new node. Here we'll take a quick break from our code to talk about call deferred. Won't spend a lot of time on this because we're already running long, but basically call deferred ensures that adding something to or removing it from the tree happens outside of the physics processing. The idea being that during physics processing, something that has an area 2D or a collision mesh or something like that would cause runtime errors if you were trying to manipulate it within the tree during physics processing. So call deferred simply says after we're done with the physics processing loop, then we'll go ahead and add this child to the tree. Back in our code, if we did find our parent and it wasn't null, we have now successfully added our restored node as a child of that parent. If we did get null back, it means that we couldn't find the parent. So we're going to push a warning basically saying we couldn't spawn where we thought we could, it was not a valid node path, and then we're going to attempt to just spawn it as a child of the currently running scene, which should be fairly safe. So we're going to grab our main scene, which we can do with getTree.currentScene as node, and this is going to return, if we're running main.gd as our main level, it will return that main node that we see in the running hierarchy. Then we're going to say, hey, we're trying to spawn at level owner whatever so that we can figure out what went wrong in debugging. And then again, we're just going to call deferred, add child, the restored node. And this will place the dynamic objects that are reinstantiated as children of the currently running scene, which is probably where most dynamic objects are going to be anyway, so we can consider this relatively safe. Now, I've seen a couple of tutorials that say just to add it as getTree.root, right? And you don't want to do that because if you add it as a child of root, remember that your currently running level exists as a child of root, and your autoload exists as a sibling of your currently running level. Most of the stuff that's in your game in the current level is going to be a child of the currently running level, in this case main. So you got your player, you got your exit, your enemies, and these enemies are the dynamically spawned enemies that we're trying to restore here. So if we accidentally said, I want to add our newly instantiated enemy as a child of getTree.root, it's going to put it up here as a sibling of the currently running level. And while that may work while the level exists, as soon as you go to reload or restart the level, you're going to have these kind of immortal enemies that exist outside of the current level that won't get wiped out. And that could lead to some really weird behavior. So getTree.currentScene seems to be the safest way to go for now. Then moving on to if we're not dynamic, which means we're static, we will try to find that static node by the unique group name that we had in our requirements. Remember, we stored that unique group name in our node source for static nodes, so we can call getTree.getNodesInGroup, which returns all the nodes that are a member of a given group, and we'll store that in our group nodes variable. There should only be one if it's truly unique. So we will do a sanity check. If the length of those group nodes equal to 1, we're good, and our restored node becomes the only node in that group. If that wasn't 1, then we'll never assign a value to that restored node, and it will still be null from where we declared it up here. So if it's still null, we're going to push an error saying, hey, we didn't find our node in the unique group. And since we pushed an error, we'll bail out of our currently running method. Now, if we're still good, we have our restored node, and whether that node was dynamic or static, we have a reference to that node, and we can simply call the method that we declared as loaded in there and pass the node info back into that node. And this will be that custom dictionary that we were talking about. And remember that the node is responsible for handling its own custom data. This is where we'll go on to restore, position, etc. And that takes care of restoring our saved nodes. Let's move on to the next section. Now moving up to our save and load game methods, these are the functions that you'll call from your user interface or whatever part of your main game loop is going to be responsible for the saving and loading of games. We do have the option to pause and unpause when we're saving and loading to prevent stuttering. So the first thing we'll do is basically wrap whatever we're going to do in a paused true and a paused false. And then we need to do the same thing for our load phase. For the save side of things, it's going to be fairly short. All we do is declare our save info as a variable, run it through our gather save info function, which we declared below, and we're going to make sure that we're casting that as a global save template for type safety. Then we are going to create a dictionary using our built-in toDictionary function, and that will give us the data that we need to spit out to file. Then we're going to feed that dictionary into our save to file function. So the flow here is we gather all of the save data, convert it to a dictionary, and spit it out to a JSON file that is human readable. For the load side of things, it's going to be a little bit more complicated, but not too much so. We're going to declare a variable to hold our dictionary that we load from file using our existing method. Then we're going to create load info, which is a new global save template. Then remember, we returned a Boolean on our from dictionary method in our load info, our global save template. So we're going to go ahead and try to convert back to the template or class from the dictionary. If that fails, obviously we're going to push an error. And we have to add a little bit of extra logic here. If we are paused and we push that error, we want to make sure to unpause the game before we bail out of this particular method. Since we're stopping further processing and returning at this point, we don't want the game to hang up just because we had a problem. If everything's good so far, basically we're going to go ahead and check that our current scene is equal to the scene we expect to be in our load game. If it is not, then we are going to call deferred. We explained why that's necessary, because we don't want to be changing scenes in the middle of physics calculations, etc. We are going to change the scene to a file, and we are going to load the scene path that we have stored in our current scene variable within our save game. Now remember that if we were not working with an autoload right here, we would run into problems because this whole script would reload once we change scenes. Since we are working with an autoload that exists outside of our owner scene, this is fine. Lastly, we will call deferred once more, restore saved nodes, and we'll pass in the load info. And if you remember down here, restored saved nodes takes that info in and handles through going through the call group and restoring saved information to static nodes and respawning dynamic nodes. So that will finish up our load game, and that's really the end of this whole script here. Of course, we want to remember to unpause our game, and that'll do it. In a moment, we'll create a short example script to show how this is actually implemented within the objects themselves. For now, let's just kind of go top to bottom and do a quick summary of all this code we've written. We've created a script that extends nodes so we can use it as an autoload. This allows us to perform our saving and loading outside of the currently running tree in case we need to switch levels or something like that. We have a constant to track our version. Then we have some configuration options down here. We call this default save name because if you look down at the save and load functions, we allow the save name to be passed in as a string and override the default. This is to allow the developer who may want to save multiple files to provide their own save game name without having to come back and heavily modify the code. We're also storing the group name that we're going to use to call the individual objects that want to be backed up during save. We have a configuration option to pause the game on saving and loading. This is available to allow the developer, who may have their own pausing and unpausing logic, to turn this on and off. We then store the three methods that we're going to use in our individual objects during the saving and loading phases. This is to prevent typos and kind of help us remember what's going on. Moving down to the saving and loading methods, these will be the functions that you will call from your user interface or main game loop, whatever is handling the save and load functions. On the save function, we are going to pause the game if we need to. We will gather save info from the individual objects. We will convert all of that to a dictionary so that we can save it out to a file as human readable JSON, and then we'll unpause the game. Loading is just about the opposite. We're going to pause the game. We're going to load that dictionary from the file, create a new template, and convert that dictionary into the save game info template. Then we do some basic error handling. And then if we're not in the right scene, we're going to change to the correct scene. And finally, we will restore that saved information to the nodes that need it, and we will unpause the game. For our object interaction methods, we have gather save info, which will create a new information template. We will store the current scene so we can switch back to it later if we need to. We will call the group that we've designated to hold our objects that need to be saved, and we will have them use the method SaveRequest to submit their information to the object array in our template. Restoring will have us call the group and tell them to prepare for loading. Dynamic objects will delete themselves at this point, so then we sort nodes by priority. We will iterate through those nodes, highest priority first. Dynamic objects will have deleted themselves, so we will reinstantiate them and then pass their information back to them with a little bit of sanity checking here. Otherwise, if it's a static object, we will make sure that only one object exists in that unique group, and then we will pass that object's information back to it. Moving down to our modular file interaction methods. Remember, these are modular to allow us to later convert to storing in the cloud or whatever. We are going to take our dictionary that we have previously converted from our template. We will convert that to a JSON string and store it out to file. Loading is just the opposite, where we'll read in that JSON string and then parse it back into a dictionary. And finally, we have our subclasses that we've declared. Our global save template is just going to store our version and scene path information and an array that will contain saved information from our individual objects. We have a submethod here to sort our nodes by priority, convert our template to a dictionary, read a template back in from a dictionary, and then we move down to our node template here. And basically that is going to take in some mandatory information. Are we dynamic? Where'd we come from? Who's our parent? And what order do we need to be restored in? We will allow the individual objects to store their own custom dictionary, which must be handled within the object's code itself. And this node template will also have submethods to convert to and from dictionaries. Then we'll throw in a couple of data helper methods. And lastly, we have a simple utility to make our sanity checking a little bit easier to program. That does it for our main save game script. Now let's move on to our example usage script. Over in our file system, we will create a couple of scripts for these examples. One for static and one for dynamic. And we will open those both up for editing. We'll start out with our static node. We will make this a node 2D so that we can have a position to store. We also will throw in a custom health variable just to have some custom data to track. And then we will just come down here and start filling in our three mandatory methods. We will start off with our save request method, which will take in the array in our main save template that we will be appending our information to. We will create a new node template. We will declare that we're static by setting dynamic to false. We will set our priority as 1 so that we can be loaded first. We will set our unique group. Remember, this needs to be a single member group so that we can find this static object when we need to restore information. We will store our parent's path. And lastly, so we can store our health and global position, we'll need to create a custom dictionary. We will set our health as a key value pair in that dictionary. We will also store our global position as a key value pair in that dictionary using our built-in vector2 to array data helper. Then we will add our dictionary to our save info template. And lastly, we will append our save info template to the main array. Down in the load request phase, we are not going to do anything because we're not dynamic and there's nothing complicated to prepare for during the load. Moving to the actual load phase, we're going to take in a node template that should have the same information that we submitted during the save phase. First, we're going to extract our custom dictionary from that template, restore our global position, again using our data helper, and lastly, we will restore our health based on the information in our custom dictionary. Note that here we are setting the value of health directly to the value that was in the dictionary, but in practice, be sure to use setters and getters, because if you have like a health bar that's a visual representation of your health, and that depends on the health changing, plus or minus or what have you, you're going to want to use a setter or a getter to recreate that behavior as you're restoring that information from your save game. And because we spent so much time modularizing our main save game script, that's all there is to it on the static side. Moving on to the dynamic side, let's also convert this to a node 2D, and then move down to our 3 mandatory methods. First, let's create a target variable so we can pretend we're the enemy who is currently tracking the player. Then on our save request, it'll be largely the same. We'll take in an array of node templates. We will create our own node template to store the save information. We are dynamic, so we will set that to true. Our priority is 0 because we'll be loading after the player. And finally, our node source will be our scene file path, so that can be used to reinstantiate us on load. Lastly, we will get our parent and store that, and create our custom dictionary. First thing we want to store in our custom dictionary is our target. We will make sure that is not null since the target is a node. We will set the target node path key value pair in our save dictionary to whatever our target is, .getPath. This will return its path in the tree. Lastly, we will save our global position as a key value pair in our custom dictionary using our data helper. Then we store our custom dictionary in our node template and append it to the array. Down in the load request phase, we are dynamic, so we're going to want to remove ourselves from the tree to prepare for all the dynamic objects to be reinstantiated. The safest way to do that is to first remove ourselves from our parent and then simply queue free. Down in the actual load phase, again, we're taking in the node template that should have the same information as the node template we submitted for save. We are going to extract our custom dictionary, restore our global position using our data helper method, and then, since we only stored the target if it was not null, we will verify that the dictionary has the target path in it, and then reset the target using getNode or null. This should be safe for most situations. And again, since we put so much effort into our main script, it's doing all the heavy lifting, and this is all we need to make this object save and load correctly. Back in our boat mines game, I will create a very simple save UI, and then we'll just add our save game project to this existing game to show how easy it is and that it works. First, let's just create a folder, and we will call it global save. And then we can find our files and copy our 3 scripts in. And don't worry about all the errors you'll get, because we basically need to put these in the right place and then go to Project, Project Settings, Autoload, find our script, make sure that the name is correct, add it, make sure global variable is enabled, and then close. And then if we play our game, all those errors should go away. Now that we've got our script dumped into autoload and ready to go, we can take a quick look at implementation. Over here for our save UI, it's just a couple of buttons under a parent with a script attached, and you can see that I've already done the signal wiring for the save and load buttons. The hide and show is just a little trick to remove focus, so that hitting the spacebar or something won't accidentally activate a button. And all we have left to do for this particular part is to connect our global save, save and load methods to this controlling entity. We will go down here and we should just be able to start typing global save. It should auto-complete. We will hit period, and then we should have a save game method there. We can do the same thing using Control C and Control V and change this to load game. And that's it for this part. Notice we're leaving the parameters blank for the save game and load game functions. This will cause us to use the default save name that we have in our existing script. Let's start the implementation with our player, who is a static entity. Let's take a look at what we're going to want to save when we save the game. And basically for the player, it's just going to be the position and the health. And you'll notice for the health variable, I've implemented a getter and a setter. And basically, if we play the game, we can see that we have a health bar following our player around that updates when we either hit a mine or drag against the wall. In order to avoid a bunch of extra code in our save and load function, we use the getter and setter to handle updating the health bar, and that allows us to merely assign the value back to this variable in our load phase. Remember that we need a couple of mandatory groups to make this work, so we're going to make sure that we have our player's root object selected. We're going to go to the Node tab, Groups, and then we'll use global save for the group that's going to hold all the objects we want to save, and global save player to hold our unique symbol member group, since player is a static object. So we will just add both of those groups. And then with those groups in place, all we need to do is to open up our example script for the static object. We're just going to copy these three methods, go back to our player script, Control End to go down if you're on Windows, and Control V to paste that in. Now, since we had our health variable, pretty much this example script will work without any modification. Stepping through it really quickly, we're creating the template, making sure we're a static object, setting our load priority. This is the group that we added ourselves to, and our parent. This is our custom dictionary that's going to hold our health and global position. And then we are not doing anything on load request. And when we actually load, we're just grabbing our dictionary, restoring our global position, and restoring our health, which will update the health bar because we're using the getter and setter. Then we just need to save our script, go to play the game. We should be able to save the game here, and then we'll take a couple of hits to update our health bar, and then when we load the game, we should pop right back into the same position. And you notice that the mines are not updating when we load the game, and that's because we haven't implemented that script yet. So let's go ahead and do that now. We will head over to our mine entity. We will select the root node. We will go over to our groups and we will add it to the global save group. And we should not need a unique group because this will be a dynamic object. Then we just open our dynamic example script. We will select the three mandatory methods. We will move over to our mine script, go to the end, make a little bit of room here, and paste our three methods in. You'll notice some errors here because this is not the kind of enemy that we had where it's tracking a target. So we can just get rid of those lines because all we're really going to do for this one is to save and restore our global position. Scrolling back up just to make sure we don't have anything extra we need to add, and we don't. So let's save our script, play our game, and we will move around, save the game, take a couple of hits, and then when we load the game, we'll notice that the mines are also going back to their original positions. Close that out, and now we can move on to the torpedoes. And since we're getting into a good rhythm here, let's just find our torpedo script, go to the end, paste in our 3 mandatory methods. We will get rid of the target lines like we did before, since all we care about for the torpedoes is the global positions. We'll go back over to our Node and Groups tab and make sure that we have added this to the global save group, and then we can save everything, play the game, and we now should be able to move around and fire a torpedo and save the game. We'll take a couple of hits, and then when we load the game, our boat, our mines, and our torpedo all go back to where they were when they saved. Now let's take a quick look at our save file format. If we go back over to our script window and look at our global save, we see that when we are going to save the file, we are prepending user:// If we go over to Atom and go to File and Open File, on Windows, the user:// guarantees a writable folder, which is in our app data. So we just go to %appdata%. That'll take us to our roaming directory, where we can find the Godot folder and the app user data folder. Here we'll open up our Acorn Save Test folder. That's because this tutorial originally started out with the squirrels and the lemurs, and I decided to do the boat mines project later on and forgot to change the name. Then we can open up our save file, in this case globalsave.json, and here is the array that contains our saved nodes. Here is our player, who is a static entity with a load priority. Here's where he was in the hierarchy, and here's our global position with the X and Y that we converted with our data utility. We're also storing the health. Moving down, we can see the mines that were on the screen and the torpedo that was on the screen. After our individual objects in the array, we see the global data that we saved with our scene level and the version number. This gives us a nice human-readable save file in JSON format that we can dump to disk, store in the cloud, or even use to interact with the REST API. Now, the sharp-eyed among you would probably have noticed that we didn't do anything for the progress bar, so the progress bar was continuing to advance even as we are saving and loading. Also, the mines have an exploded state, and we didn't do anything with saving and loading to account for that, but we're way over time here, so we're not going to go back and fill in all the little details. You guys should get the idea by now. Before we summarize, I just want to add, this takes a lot of time for me to make these tutorials, and I need to know which tutorials are benefiting people so I can put more effort into those areas. So if this tutorial was helpful to you, please take just a moment to like and subscribe so I know where to focus my efforts. Oh, and one last thing, we should probably just make sure our level change logic works real quick. So let's head over to our level script, and we are going to just change the progress timer to, let's say, 10 seconds to make it a little bit easier to get through the level. We'll play the game, and we will save around here, and then we will get through the rest of the level, and the level ending sequence will happen, and we will change to level 2, which is just basically the same thing except with rocks and mines. And then we will go ahead and load the game again, and we've run into an error. I'm going to pause real quick and figure out what that was. Okay, so what happened here was when we were attempting to change the scene and call our restore save nodes method, it was attempting to restore our saved nodes before the level was completely loaded. And there's a couple of fixes we can do here. The first one we can try is we can come up to our load game method, and here is where we are determining if we need to change the scene. And all we really have to do here is to put in a short timer to give the scene time to load before we attempt to restore our saved nodes. We can do that by simply putting await getTree.createTimer, throw in like 1/10 of a second or something, and await that timeout. And with that in place, we can play the game, and this should allow us to get through our first level. And when we transition to the second level, we should be able to load back into the first level, and hopefully that 1/10 of a second will allow the level to load into memory before we attempt to restore our nodes. And we can see that that works. So that's okay. But that doesn't really sit well with me because we're kind of cramming a static timer in as a band-aid here, and we may have somebody with a slower computer that exceeds this timeout, or a faster computer that doesn't need it. I haven't had issues with this when I was testing, and it just kind of popped up while we were doing the tutorial. So let's get rid of this line, and let's put something in that does sort of the same thing, but is dependent on something that we know is going to load when everything is ready. So we're just going to create a variable. It's the same thing that we use for a comparison up here. We're just going to call it current level path, and we will grab the current scene file path, and we will do a while loop while it is not equal to what we want. We are going to put in a very, very short timer, 1/100th of a second. This is just to allow stuff to process, because if we don't have this, the call defers will never get around to executing. And then we're just going to say our current level path is again equal to getTree current scene file path. And what this short little loop is going to do is just make sure that we've exited our level 2 and loaded level 1. Or more specifically, we've exited the currently running level and loaded the level that we're supposed to have in our save game info. And then we're just going to save that script real quick. We're going to run the file. I've dropped the timer back to 5 seconds just to make this a little quicker. We'll go ahead and save here. We'll let the level transition happen. And then when level 2 is loaded, we'll move around a little bit, make sure we're really in level 2. There's a rock, and then we can hit load, and we're back in level 1. And everybody's happy. And we'll go ahead and we will get back to level 2. And we will save in level 2. And then we can exit the game, play the game again, and in the middle of level 1 we can hit load and we're back in level 2. So with that little loop we've solved our problem, and this is ready for prime time. Let's not forget to copy all of the additional code that we just did, and we need to be sure to go back to our original Godot project that we are using as a template and go back to the same place in our global save GDScript. And then in that same place, we will insert the fix that we just did. Wait for that error to clear. And now our copy and paste template has the same fix and should work the same. And with that, we're done. We have created a wonderful reusable utility that we can merely drop into any project, and with some minor code changes we can have any object in that project submit its own save game data. It will handle its own save game info on save and load, and we can implement this with very little back-end coding. I wasn't joking when I said this was going to be a deep dive. I'm sorry it ran so long, but hopefully you got something out of it. As always, if you have any questions or you have an idea for the next Godot tidbit, please let me know in the comments. Thank you guys for listening, and have a good day.